Okay. So basically, we talked about normal PN junction, right? So the normal PN junction is a passive device, right? So basically, you know what is a passive device, right? So if you are applying voltage across it, let's say V, and there will be a current, and we know that current is nothing but I0 times exponential QV by KT, right? And minus 1. Okay. So so this is a passive device because you are giving a voltage across the PN junction and we are getting a current, right? So there is no way we could change the current without changing the voltage, right? So this is a passive device, but uh, for electronics, right? So for electronics or integrated circuits, we not only need passive devices, we also need active devices, right? Um, when you talk about active device, so if you think of active device, so basically, so if so so let's say this is a device, let's say device, so this is any device. So if I'm applying a voltage, I'll get a current, right? So right, but in pass active device, I have a control terminal, right? So this is a control terminal, right? So my current is not only function of voltage but also the function of the control voltage, right? Even if my voltage is constant, even if my voltage is constant, the voltage applied across the device is constant, the current can be changed by changing the control voltage, right? So this is an active device, and active device have a lot of application in electronics and mostly in integrated circuits. So for example, when you're talking about a switch, right, a normal switch, right? So so normal switch, so basically uh, you are applying a voltage, right, and you are getting a current, but this here by controlling the switch by a control terminal, you could control the current, right? So whether the whether I am getting, let's say I have a load here, I have a load here. So by controlling, if I turning the switch on, that means if my by applying some control voltage, I could turn the switch on, and the current will go to the load. If I remove this control voltage, the switch will be off, and there will be no current going to the load, right? So basically, we in the digital circuits we use switches, right? So our transistor, our MOS transistor, our bipolar junction transistor, we are mostly operating them as switches, right? And also in when you talk about analog ICs, right, analog IC design, so when we do amplifiers, right, so there we are using using your using also active devices, and basically you use active devices as the current sources, and by controlling the voltage you could change the level of this current source, right? So uh, the main point here is uh, diode is a passive device, right? PN junction, normal PN junction is a passive device. So, but we need active device for our applications. So, when we talk about active device, mostly we talked about devices with three terminals. One is input and output terminal. Also, we have a control terminal, and mainly in the active device we have transistors, right? So we call those device says transistors, and we basically have two kind of transistors: bipolar bipolar transistor and MOS transistor. Okay, so so all of you might have done some might have studied a little bit about bipolar junction transistors, and so if you see, if you so bipolar junction transistor, the symbol of a bipolar junction transistor is like this. So I have, this is a three terminal device. So I have emitter, terminal, base, and collector, right? So here if you see your so since this is a three terminal device, right, so we have three terminals. So we have, and we generally call it a two-port device, right? So three terminals, we have two ports. I have an input port and I have an output port. So basically this is my input port here between base and emitter, and base and collector, and this is my output port, right? So here in this case, if I'm applying, let's say this is a common base configuration, or let's say I'm applying the voltage, this is the VCE, this is the voltage across the device, right? And I'm getting current IC, right? Collector current. But by controlling the base terminal here in this case, right? Okay, controlling the base terminal or voltage applied to the base terminal, I could control the current. So current is here in this case will be a function of voltage across the device. So current will definitely depend on the voltage across the device, also the control voltage, right? Right. But here, but please keep in mind, uh, in this case, when I'm talking about a control terminal, so if you look at base here, right? So base is our control terminal. That is the terminal which is controlling the current flow between collector and emitter, right? So, so couple of things, right? So this terminal or this base should not consume a lot of power, should not dissipate a lot of power, because then basically if I have a control terminal and control terminal is consuming a lot of current or means or dissipating a lot of power, then this will not be helpful. So basically what I want, if this terminal has a current IP, right, base current, right, so this current should be as low as possible, because I want to control the current flowing between collector and emitter with less effort. Less effort means I don't have to consume that much power to control the current flow between uh, collector and emitter. Okay, so this is one case. I means your base current should be low, right? So because okay, and so our out current is flowing between collector and emitter. So there should not be any difference, right? So basically, there should not be any drop inside the device. That means the collector current should be equal to emitter current, right? So these are the two conditions when we are designing an active device, right? So when I talk about designing an active device, it's not about doing some circuit design. It is about designing the device itself, right? How do you design the device? Because from the outside, it looks like I have a E, B, C, but when you look when you go inside the device, we have also seen in the PN junction, right? So, right. So if you go inside the device, how to design that device so that your base current, in this case your control current in the control terminal is very low, and your IC, your collector current is equal to emitter current, right? Okay. So so when you talk about bipolar junction transistor, I have two types of BJTs. I have one NPN, and PNP, right? So basically, when you talk about bipolar junction transistor, so bipolar junction transistor has two junctions, right? We when you discuss about PN junctions are mono junction devices, right? So they have only one junction, PN junction, right? One PN junction. But bipolar junction transistor has two PN junctions. So if you look, so I have two PN junctions. So I could create these two PN junction by doing NPN. That means I have one junction here and one junction here. So I have two junctions. Or I could do it using PNP, right? So in that case, I have one junction here, another junction here, right? So if you want to have a device with two junctions, two PN junctions, so I could have NPN or PNP, right? So we have two kinds. So that's the reason we have two kind of bipolar junction transistor. We have NPN and we have PNP transistors. Okay, another thing here is there are three regions. I have an N region, I have a P region, I have another N region, right? So I have basically three regions here, right? So if the materials of all those three regions are same, the semiconductor material is same, that semiconductor material of N region is same, P region is same, and N region is same, then we call it homo junction, right? So basically NP, so let's say if this is silicon, this is also silicon, this is silicon, right? So both the junctions are silicon junctions, right? Even if this is NP, but the material is same. So these are called homojunction devices, right? So generally when I talk about bipolar junction transistor, I mean they are homojunction. Homojunction means the material of N, P and N are all same, right? But it is possible that I have metal 1 here, metal 2 here, metal 3 here, right? Or metal 1 here and both these metals are metal 2, or metal 1, metal 1 and metal 2, right? So these are all, we can have different combinations also, right? But here you see, since the semiconductor material is changing from P to N or N to P, so these are all these we call the heterojunctions, right? And we have not yet discussed about heterojunction, but when you means we'll discuss when you means in bipolar junction BJT, we'll discuss about heterojunction devices, right? So this is a heterojunction bipolar junction transistor, right? And we popularly call heterojunction bipolar transistor HBT. So this is a bipolar transistor. It's a homojunction. So homojunctions are called bipolar transistors, and heterojunctions are called heterojunction bipolar transistor (HBT), right? And heterojunction bipolar transistors are more popular now. And in the modern bipolar transistor, all are heterojunction transistors, right? So when you talk about power transistors, also, right, they're also heterojunction bipolar transistor. So only in the CMOS process, so we have some parasitic bipolar junction transistors. They are currently used in circuits. Otherwise, if you're fabricating standalone bipolar junction transistor, mostly we are fabricating heterojunction bipolar transistor nowadays. Okay, so we'll discuss about homojunction. We'll discuss about heterojunction bipolar transistors in next few classes. Um, Okay, so how does a bipolar transistor look like? So this is a typical means typical. This is again a homojunction, right? So this is a homojunction bipolar homojunction bipolar transistor, right? Uh, right. You see, means I have means the semiconductor material is silicon only, right? So this is a homojunction device. So if you look at a bipolar transistor, if you take a cross section, it actually looks like this. I have three terminals: emitter, base, collector. And so but here you see, this is the cross section, right? um, um, so you have let me copy this. Right. So so when I talk about NPN junction, so basically we are talking about this part here. So if you go from emitter base, if I go from top to bottom here, right? So I have a junction here, right? NP junction and another PN junction here, right? So this is my actual transistor, but I have to, because when you fabricate a bipolar junction transistor, all the terminals, all the contacts that you're taking, right, emitter contact or base contact or collector contact, so they will be on the top surface, right, top surface of the silicon, right? So that's the reason we have this base is taken as, so you again have a P plus regions, and we take the base contact there. So this yellow region that you see here, that is your base part, right? So your base part has two things, right? So we have intrinsic base region, right? Intrinsic base region, right? And we have extrinsic base region. So extrinsic base region, right? So intrinsic base region is very important because that defines the characteristic of the transistor, right? When I talk about intrinsic region, so this part is your intrinsic region, right? So this part here, you see, if you do this part here, right? So I have my NPN, right? So this is your intrinsic device, right? Right. So this is your intrinsic device, right? So you see you have N, so NPN. So this part is your intrinsic device, right? But you need extrinsic part to collect the current, because I also I need to connect the base, right? So I cannot put a contact here. If I could put a contact here, then that will be really good. But in the real devices, I could not have a contact here. So I have to put the contact at the top. So this region here, this region, extra region, this is the extrinsic part of the device, right? So this is the extrinsic part of the device, right? Similarly, this part here, right? This is the extrinsic part, right? This is the extrinsic part of the device, right? So here you see I have two base contacts. I have one emitter contact. I have two base contacts. In many modern transistors, you have only base contact in one side. You don't put the base contact in the other side. But here it is a symmetric device, right? So if you take a cross section here, if you take cross section here, so left hand side and right hand side are mirror image of each other, right? And the most of the bipolar transistors are like this. You have two base contacts, but if you have a space constant, and many times to reduce parasitics in very high frequency transistors, uh, so there you remove one base contact, right? Okay, so I have an intrinsic region, I have extrinsic region. And similarly, if you look at the collector, right, this part, this collector, this part is your intrinsic part, right? Because this defines the characteristic of your bipolar junction transistor. But the other region, right, because you have to take a contact, so n plus, so this region, so whole this region, this is my extrinsic, right? This is the extrinsic part for the collector, right? And this region here also the extrinsic part of your collector, right? So you see emitter, here emitter do not have an intrinsic or extrinsic part. Emitter we have only intrinsic, but your base and collector have two regions. So one is intrinsic region, one is extrinsic region, right? So intrinsic region defines the characteristic of your device, but extrinsic region will give you the parasitics, right? So because extrinsic is necessary, because you have to collect that current, because when you the collector current, your collector current will be collected, right? But because they have to collect it at the top, right? So for the, I mean, if you look at the overall operation of the device, so you have to take care of, when you're designing your bipolar device, you have to take care of both the regions, right? You have to take care of the intrinsic region as well as extrinsic region, because extrinsic region will also give you some parasitics. So, but you don't want those parasitics to be there, right? So you have to, while designing the device, you have to take care of both part, right? Intrinsic and extrinsic part. So here also I have two collector contacts. So you could also do away with one contact only. So right, and if you look at the layout, right, it's because layout is very critical, because if some of you will design a bipolar junction transistor based circuit and send it for fabrication, you have to do a layout also, right? So basically the layout, so we have emitter, right? So we have emitter area, so you have to draw. Then you have a base area, right? So actually bipolar transistors are designed like this, right? So this is your base, this is your base, and you have a collector area, right? So collector, right? So basically they are designed as concentric means squares or rectangles, right? This is your collector, right? So this is your collector here, right? So this is your emitter, base, and collector, and this region inside, right? This region here, this region between emitter and base. So these are isolation, right? So because you have to separate emitter from the base, or you have to separate collector from the base. So these are the isolation regions, right? So I have drawn these isolation regions here, right? Oxide, right? 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 So okay. Uh, so this is and many cases. So there is, see here I have shown there is oxide between emitter and base. In the modern design, we do not have emitter and base are not isolated, because we have now self-aligned fabrication technology. So emitter base there is no isolation. But actually, when the bipolar junction transistor, I mean, in 1970s, when people are drawing bipolar junction transistors, even 1980s, so it actually looks like this. So we have emitter, we have base, we have collector, and between emitter is separated by base by this isolation oxide, and between base and collector also there is oxide, right? And when we're talking about the area of the bipolar junction transistor, because area is very important, because because what is the area of the area of the transistor, right? So area of the transistor is nothing but the area of your emitter, right? So the area of your bipolar junction transistor is nothing but the area of your emitter, because the if you look from the top, right? So your intrinsic part is, sorry, your intrinsic part is this part. This part is an intrinsic part, right? Other regions are extrinsic regions of your bipolar junction transistor, right? So the area of your transistor is area of the intrinsic region, right? And area of the intrinsic region is nothing but the width of the emitter, I mean width and length of the emitter, right? However you have designed, right? Right. So that's area. So the when you talk about the area of the bipolar junction transistor is nothing but the area of the emitter, right? So that's the region. Emitter area is a very critical parameter in bipolar design, right? Because emitter area is the area of the transistor, right? Okay. So this is how how the transistor on the silicon wafer will look like, right? So, but if you take a cross section, if I take a cross section here, right, it will look like this: emitter, base, collector, right? Here you see there is no separation between emitter and base, because this is, I have taken the modern design where there is no oxide between emitter and base, but base and collector there is a oxide isolation region, right? So this is how your so if you take a cross section here, it will look like this, right? It will look like this. So you have emitter, base, collector, and see here you have, when you take the contacts, right? Because your this is on the silicon, but then you have metal lines, right? You are taking your terminals out, right? So your contacts will be here, right? So you will have a emitter contact here, and collector contact will be also distributed, right, across this ring, and the emitter base contacts will also be distributed, right. So right, so basically uh, yeah, so these are your contacts, right? You will see here also you have mirror. So if you take a cross section here in the vertical direction or horizontal direction in the middle, so these are mirror images, right? This is a symmetric transistor layout, right? So basically bipolar transistors are symmetric uh, transistors, right? So if you take a cross section, if you take a cut at the in the middle, whether it is a vertical cut or a horizontal cut at the middle, so it is same, right? Both the parts. Okay, so are there any questions here, or is it clear to everybody? Can you visualize this?
Yes, sir.
Yeah. Okay, so anybody else? Aditya, Monica, Neeraj, and Nishant, Om.
सर सर यू सेड द इंट्रिंसिक रीजन, इसका मतलब सर ये सिर्फ इतना ही है ना, क्या ये अंदर वाला पार्ट है?
So intrinsic region is this part here, right? So if you look at the cross section, your intrinsic region is this part, right? So you see the intrinsic region is this part here, right? Right. If you look from the top, this emitter region is only the intrinsic region, right? So similarly, in the layout, top layout, if you look from the top, right, this is the layout what you will have to laid out on the silicon, means for fabrication. So this is your intrinsic part, right? Right.
सर
And the
जनरली
area of the bipolar transistor is nothing but the area of your intrinsic region, right? And that area is the area of the width of the emitter and length of the emitter.
yes sir, but the general thing is that the intrinsic means there is no dope at that
Intrinsic
point.
region is not doped. No, it is not. How do you mean by it is not doped, right?
Oh, yeah, yeah, it is means that it is inside the, it is the part of the that device.
Yeah. You so it means we'll discuss these things. Means in the next few slides. But here you see these are doped, right? This is N plus region, and this is P region. This is N region. These are doped, right? So you
Yeah.
see, means this is a complicated structure to fabricate, right? If you look at this is a cross section I have shown, you could see different color coded things, right? So you see, this is not very straightforward to design it. It is also complicated. I mean, it's not very complicated, but we have several steps, right? So we have implantation, oxidation, deposition, every fabrication steps were using to fabricate a bipolar junction transistor, and finally it looks like this, right?
Sir, in this cross section, like you have shown n plus p and n. Sir, generally when we studied about BJTs in lower classes, we consider p, that is base region, to be of very small width. So it would be same here also.
Yeah. It will be same. So okay. Yeah. So we'll come to this point. So this is yeah. So basically, okay. So here, see the okay. Means I also want to clarify something, right? When you look from the top, right? So there is a width and length of each means of the transition emitter area, right? But when you take a cross section, so I have these regions are actually thickness, right? So basically, this is my thickness of the base region, right? And this is the thickness of the emitter region, right? And this is the thickness of my collector region, right? But in the books, actually, since this thickness, this TE or whatever written here, TB and TC, we call it the width, right? Actually, current flows from in the so bipolar junction transistors. When you go to MOS transistors, current flows laterally, right? But in the bipolar junction transistor, current flows vertically, right? So current flows from emitter, base, collector, right? So you see EBC, there is vertical junctions, right? So basically current flows from top to down or bottom to top, right? So that's the reason these are called in the so many means most of the books are these are called the width, right? Because this is the width when the current flowing direction, right? So these are also called the width of the base region, width of the emitter region, or width of the collector region, right? But actually, in the fabrication terminology, these are the thicknesses, right? And the width will be, if you look from the top on the silicon, so it looks like this. So your width and length will be the of the width and length of the layout region, right? And yeah, so width and length will define the area. But also, means let's use in this class, let's use the thickness, right? Thickness of the emitter region, thickness of the base region, and thickness of the collector region. We'll not use the width term there, right? So I'll tell the thickness of the base, and when you're telling about the width of the base should be low, I'll tell thickness of the base should be low.
Yes, sir. Okay.
Yeah. So because these are only the thicknesses of the semiconductor part, right?
So, why are the doping levels different in the extrinsic and the intrinsic base in the collector region?
No, the doping levels are not different. These are N. But only thing when you're taking the contact here, sorry, when you're taking the contact, because you need a ohmic contact. So we have not yet discussed the ohmic or Schottky contacts. For the ohmic contact, you always have to take contact from the highly doped region, right? So what you do, you have N, but you do extra, you make it N plus so that you could have a ohmic contact, right? So ohmic contact, see, Schottky contact, your PN junction is a Schottky device. That means it only carries current in one direction, right? Right. So similarly, in the means basically you need a ohmic contact because your current can come in or go out, right? So that's the reason you need to form a ohmic contact, and ohmic contact can only be formed when you take very highly doped regions, right? Because this is a metal, right? Right? And the metal and semiconductor junctions, right? Metal semiconductor junctions will be ohmic when the semiconductor is very highly doped, right? So that's the reason I have this N plus here. This is just for the contact region, right? But when you look at the intrinsic part, right? So I don't have any change. And extrinsic part also, you see this color coded also, except this N plus region, other area is this N, right? Right. And okay, you could tell it's very difficult to have uniform junctions everywhere, right? Uniform doping everywhere, right? We'll have a graded doping because when do implantation, we'll see actual transistors even for the PN junctions, right? So what we have discussed in the class is P is uniformly doped, N is uniformly doped, right? But actually, um, I could draw it here. So let's say I have a PN junction or NP junction, right? This is N region and this is P region. So we are assuming that I have N when I talk about the doping in the N region. So this is same and the doping in the P region is same. That means if I have N region and P region, I have uniform doping in the N region and I have uniform doping in the P region, right? But that is not the case, right? So because implantation always have a Gaussian distribution, right? Basically, if you look at the cross section, so you'll have something like this, right? So I have N, you might have seen in the simulation also, right? So I have N, then I have P, right? So there is a Gaussian distribution, right? So, right? So, and this part is junction when N and P will equalize each other, right? Right? So, yeah, so uh, you'll have some non-uniformity because this parts, right? So let's say N plus okay, P okay, N ho. So these are created by N implantation, right? Implantation means you implant different dopants, right, to the silicon, then you annihilate, right? So when you do in that process, you will have a graded profile, right? And we'll discuss those things, right? But the time being, assume that N plus is uniformly doped and P is uniformly doped and N is uniformly doped. Emitter, base, and collector uniformly doped, right? Okay. Are there any questions? Any other questions? Okay. I hope all of you could visualize it. Um, okay. So now what actually is done? All right. So if I look at the intrinsic part, right? So as I told you, this is my intrinsic part, right? If I intrinsic part and put it and rotate it, right? I will take the intrinsic part, rotate it. This is what your bipolar junction transistor, because as I told you, the characteristic of bipolar junction transistor depends on the intrinsic part, right? And I'll take this part here, right, and rotate it, right? I rotate it. All right, so then we'll have N plus P N, and this is my emitter region. And assuming here that emitter is highly doped, and why it should be highly doped, we'll discuss in few minutes, right? So I have so this is an NPN transistor. So my emitter region is doped with, let's say, Ne. So in this case, the electron concentration in emitter is Ne, right? And whole concentration is emitter is Ni square divided by Ne, right? And here, as I told, let's make this thing, right? I'll tell this as the thickness of the emitter. This is the thickness of the emitter, right? And I'll tell this is the thickness of the base, and this is the thickness of the collector, right? Right? Thickness of the base, and this is the thickness of the collector, right? Let's not do the width like mentioned in the books, because many times it confuses the students, right? So okay, so okay, so now in the P side, I have Nb. So your electron concentration in the base is Ni square by Nb, and the whole concentration in the base is Nb. Similarly, your electron concentration in the collector is Nc, and the whole concentration in the collector is Ni square by Nc, right? And this is a homo junction device. So this is a homo, I mean, silicon bipolar transistor. So Ni is same. Ni, I know it will be around 10 to 10 per centimeter cube, right, at room temperature. Okay. So now we'll take this device and analyze, and after we analyze the intrinsic part, then we'll come back to the extrinsic part, right? And how extrinsic part influences the device characteristic, right? Okay. Um, all right. So before going to the device analysis, right? So let's look at the band diagram, right? Because band diagram is very important in understanding of the device. So so I have NPN. So here emitter is heavily doped, right? And collector is light doped, and your base is doped, also lightly doped. So if I do, means if I draw the band diagram, so band diagram is nothing but if I'm plotting EC and EV as a function of, if let's, this is X, right? As a function of X, right? Means with X, right? So so N side, so how will you draw it? Means I hope by now you could comfortably draw energy band diagram. But if you could not draw the energy band diagram, please practice it again and again, right? Because energy band, if you as a device, if you're doing a course on device and you could not plot energy band diagram, then it's not good, right? Okay, so means basically to draw the energy band diagram, because this is in equilibrium, there is no current flowing, let's say. So then our formulable will be constant. Then formulable, then we'll do the EC and EV of the, means we'll draw the vacuum label, we'll draw the conduction band, valence band. Then you could connect, right? So so you could connect the EC of N side to the EC of P side, and this is not, as I told you, this is a quadratic, right? So basically connect it by straight line, right? Please do not connect it in the straight line also whenever if somebody asks you to draw the band diagram, right? So because it is, then it will be totally wrong. Okay, so this is my energy band diagram. So here, since N plus P region, I will have depletions. I have a depletion region in the N side. I will have a depletion region in the P side. So I could draw it here. Let's say I have a depletion region in the N side. I will have a depletion region in the P side. Right. Similarly, here I will have a depletion region in the P side, and I will have a depletion region in the N side. Right. So so let's say this is. So if this is 0 here, right, or if I take this as 0, then this will be TE minus depletion region in the N side, which is WE, or I'll take DE. This is TE minus DE, and this is TE here, right? And this is TE plus depletion dB1, because if you look at the P region, there are two depletion widths, one in the left side, one in the right side, right? Let's left side is D plus dB1. So then in the right side, this will be TE plus TB minus dB2, right? So T plus TB minus dB2. So this part here is T plus dB, and this part here is T plus TB, sorry, TB plus DC, right? Okay. Now this, and this is the total, right? This is T plus TB plus TC, T plus TB plus TC, right? Okay. So basically, you have two depletion widths, right? So there are two junctions, right? So we'll have depletion region, and the DE, DB1, so DB2 and DC here, so they will depend on the doping. So they are functions of doping and voltage, applied voltage, right, across them, right? So right, this part we have already discussed, right? And this region here, right, this is the neutral base region, right? So this is the neutral base region, right? Neutral base region. This is charge neutral, because the, okay, and similarly you have a neutral N region also, this part, and you have a neutral collector part, right? So this is neutral emitter region, and this is neutral collector region. Okay, so so in the neutral part, your bands are flat because there is no electric field, so the bands are flat. So you see you have flat bands here, right? And in the depletion region, you have a potential, you have voltage drop, you have electric field, so you have you have a sloped band, right? Gradient band, right? The band is graded right here. Okay, so now if you look at, there is a junction, electric field across the junction, right? And the electric field is always from N to P, right? So so I'll have an electric field here also. This is, let's say, electric field 1, and I'll have electric field, another electric field E2, right? So electric fields are always from N to P, because in the N side I have a donor ions, in the P side I have acceptor ions. So you will have always from the positive charge to negative charge, right? So basically electric field is from always from N to P, right? So I have electric field E1 here in this junction, and I have junction E2, right? And this electric field again will depend on different parameters that we have discussed in the PN junction. You could actually use the same equations here, right, to find the electric field and the depletion widths, right? Okay, so once I understand this, then I have two junctions, right? So I have junction 1, which is emitter based junction. I have junction 2, which is a collector based junction, right? So I have two junctions, right? So when I talk, means basically, so every junction can be forward bias or reverse bias, right? So then I could forward bias. So basically, if you look at the options, then I have 4 options, right? Either you could forward bias both the junctions, right? Or you forward bias J1 and reverse bias J2, or you reverse bias J1 and forward bias J2, or both the junctions are reverse biased, right? Right? We have 4 options here, right? Right? So this option we will discuss. This is called the saturation, right? Because we will discuss why it is in saturation, right? So this is the saturation region of operation, saturation, and this is my forward active, which is most means forward active, right? And this is my cutoff, and this is the reverse active, right? Reverse active mode of operation, and let's say this is my forward active mode of operation. So we'll discuss what happens in forward active mode, what happens in reverse active mode, what happens in cutoff, and what happens in saturation, right? So when both the junctions are reverse biased, we call cutoff. There is no current flowing, right? So this is a cutoff region, right? So if you are using your bipolar transistor as a switch, right, for a switch operation, so let's say this is 1, 2 different modes of operation. So we operate in mode 1 and 4, right? So when you have, if you're turning on the switch, that means we are operating the transistor in saturation. When you're turning off the switch, then cut off, right? So basically, when you are operating your bipolar junction transistor as a switch, you are operating between cutoff and saturation, cutoff and saturation, cutoff and saturation, right? Cutoff and saturation, right? But if you want to use your bipolar junction transistor in analog circuits, right, where you're using this as a voltage control current source, right? Analog circuits, because in amplifiers or any current mirror or whatever, right? Any analog circuit where you're using it as a voltage control current source. So there we are mostly used in the region 2, right? 2 or cutoff, right? Either it is turned on, that means it goes to productive mode, or it is cut off, right? So so productive mode is most popular because we use your bipolar junction transistors in analog circuits, very high frequency RF circuits. So there we use the transistor in the productive and cutoff mode, right? But in digital applications, we use it between saturation and cutoff, right? And this reverse active mode is not very popular because we don't use, this case, because your emitter based junction is reverse bias, collector based junction is forward bias. This mode is never used, right? Right. So reverse active you don't use, but other 3 reasons, right? Your both the junctions are forward bias, emitter based junction is forward bias, collector based junction is reverse bias, or both the junctions are reverse bias. They are very commonly used modes, right? Okay, so in the beginning, we'll discuss about forward active mode of operation, right? So let's discuss about forward active mode of operation. Um, okay, so let's discuss about that. Again, I'll make this correction here because we decided that we'll use it as emitter thickness. This is the base thickness. This is the collector thickness. So let's use as productive mode. Productive. That means your emitter base junction is forward biased and your collector base junction is reverse biased. Okay. So again, before we go there, so I have this is a 3-terminal device, and I told you in the beginning this is a 2-port, right? So when you talk about a 3-terminal device and 2 ports, right? So let's say I have EBC, and I have this is a 3-terminal device, and I have 2 ports, right? So this is port 1 and this is your output port, right? So always emitter base is your input port, right? So emitter base is your input port. So and collector base is your output port, right? So since there are 3 terminals, I could make 1 terminal always common, right? So basically I could have your base, if my base is common, then I'll give my input voltage to emitter and I'll take the output voltage from the collector, right? So that is the common base configuration, right? This is common base configuration, and my base is common, and so basically this is my input port, right? So input port, so I'm giving my signal to the input port. Since the base is grounded or common, so I'll give my signal to your emitter, right? So this is my and take the output signal. This is my input signal, and I'll take the output signal uh, from the collector, right? And this is the common base configuration, right? Similarly, I could also do EBC. I could have common emitter configuration, right? Emitter is common, right? If emitter is common, then my input signal, because this is my input port, this is my input port, so I'll give my input signal here, right? And I'll take the output signal from collector, right? So then this is my common emitter configuration, right? And similarly, I could have common collector configuration, right? So common collector is EBC, your collector is common, but this is again my output port. This is my input port, right? Right. So here, um, since the collector is common, so you give your input signal to here, right? And you take your output signal from here. So this behaves like this. Actually, there is a little bit change. So this is becomes your input port, right? Always E and B, but your C and E, this becomes your input port, and this becomes your output port, right? Between C and right. So you see your, if you look at 3 configuration, so your input signal is always given to emitter or base, right? You never give your input signal to collector, right? Your input signal is either given to emitter or base in all those configurations, right? Common base case mein you are giving your input signal to emitter, common emitter case mein you are giving your input signal to base, common collector you are giving your input signal to base. But output signal you always take between base and collector, sorry, collector and emitter. So you, in the case of common base, your output you take it from collector. In case of common emitter, you take your output from collector. In case of common base, sorry, common collector, you take your output from the emitter, right? So this part needs to be very clear because we'll have 3 configuration: common base, common emitter, and common collector, right? So right. Um, so I have, to summarize, I have common emitter, common base, common collector configurations, right? And at the same time, I have also modes of operation. I have saturation when both the junctions are forward biased. I have forward active, I have reverse active, and a cutoff, right? So these are modes of operation: common emitter, common base, common collector, and this is region, right? So I am operating in the saturation region or forward active and reverse active or cutoff. Okay, so common emitter can have saturation, forward active, reverse active cutoff. Common base also can have saturation, forward active, reverse active cutoff. Common collector can have also saturation, forward active, reverse active cutoff. Okay. Yeah, I have only 5 minutes. All right. So, uh, okay, now I'll talk about forward active. Right. Let's discuss about forward active, because forward active is the most common configuration. Right. And let's talk about common emitter configuration. Right. Right. Um, Common emitter. Right. So that means emitter is common. So emitter is common. So if I want to have forward active, that emitter based junction has to be forward biased. So forward bias, your emitter is common. So I'll not give any voltage to emitter. So, and if I want to make this emitter based junction forward bias, I'll give a positive voltage here, right? So in this way, your emitter based junction is forward bias, and this voltage is VB. Then this voltage will have VBE, right? So VBE is the voltage between base and emitter. The input port, the voltage is VBE. Okay. Similarly, if you look at output, so basically your collector base junction needs to be reverse biased. So I have used a positive voltage, right? So here you see this junction. So basically I have to reverse bias it. So I'll give a forward bias VC, but to make this junction reverse bias, your VC should be more than VB, right? Otherwise, this junction will not be reverse biased, right? So you see your PN junction here, this junction here, PN, this junction. For forward active mode of operation, I have to reverse bias this junction. That means your VC should be more than VB, right? Right. And to forward bias it, that means you have to apply sufficient voltage that this junction is forward bias. So for silicon, we have already discussed. If you want, okay, this is sufficiently forward biased, that means we are applying around 0.6, 0.7 volt, right, across this color emitter based junction, so that it is forward biased. Okay, so this is the forward active mode of operation, and we'll see device operation in the forward active, and we'll see how the doping, and we'll derive the equation of currents and all those things in the next class. I have only 2 minutes here. I do not want to start this today. So anyway, we'll have a class tomorrow at 10:30, and we'll derive the current equation of the bipolar junction transistor tomorrow morning. All right. So I think I should stop here today. And are there any questions?